Everyone, in today's lecture video we'll be discussing about K-map. Firstly, we'll discuss what is K-map, what are the different types of K-map, and what are the applications and what are the advantages of K-map, including the types of K-map. So first, let us try to understand what K-map is. So let us consider any Boolean expression. In simpler terms, we usually used to simplify a Boolean expression by using different laws. What could these laws be? For example, associative law, or commutative law, or distributive law. Or we can use De Morgan's law or involution law to simplify the Boolean expression. But these are only applicable for simpler Boolean expressions. However, if we're dealing with a 3 variable or a 4 variable K-map, Boolean expression, we need K-map. So what is K-map now? A K-map is nothing but a tabular or a pictorial representation of the Boolean expression. So let's move ahead. Okay, so this is how a K-map looks. Here we're discussing about a 2 variable K-map. So first let's try to understand what are the different types of K-maps. We have a 2 variable K-map, a 3 variable K-map, and a 4 variable K-map. So in the given representation, we have 2 variables x and y here. The cursor shows x and y here. So accordingly, we plot the truth table for this x and y for 2 variables. Let us try to understand the 2 variable K-map here. So how do you find the number of squares here? Each squares are cells here. So we have 2 variables, so that means 2 to the power of n. 2 to the power of 2 is nothing but 4, so we draw 4 squares here. And let's try to understand the labeling of the K-map. We have 0, 1, 0, 1. This is for the x variable, this is for the y variable, for the x and y variable. Now, very important to understand that we're dealing with SOP expressions, meaning sum of product expressions. So here we have it is represented by small m. So m0, nothing but 0, m1, 2 and 3. So once we plot the K-map, we go through these simplification. Moving to the next slide. Here we come across a 3 variable K-map. In a 3 variable K-map, one thing we need to note is that we have the concept of gray coding. Here in this K-map, 3 variables, so we have x, we have y and z. Here 0 0 is again xy, 0 1 xy, 1 1 xy and 1 0 xy, 1 0 y and z, sorry, y and z. So here at m0 we have x, y, z. That should be denoted as x bar, y bar and z bar. Wherever we have 0, that simply signifies a bar notation, and wherever we have just 1, it is x or y or z based on the variables we have in the K-map. So similarly, as I have told, 2 to the power of n, 2 to the power of 3 here for 3 variable is 8. So we have 4 plus 4 equal to 8 number of cells of squares. xy represented here. Similarly, we have the binary notation here as well as here. Now let us try to understand what is gray coding. In gray coding, the second and the third term gets interchanged. So, beg your pardon, it's the third and the fourth term. So we start here 1, 2, 3 and 4. So based on the order 0 0 0 1, it should be 1 0 and 1 1, but here we apply gray coding. So that means 1 0 goes here and 1 1 comes here. So the third and the fourth positions are interchanged. Here it remains same. We have only one variable, that is x, so 0 and 1. Now in this example, what have they given? They given a function with x, y, z 2 3 4 5. So first step is to plot the truth table, that is for x, y and z respectively. After that, We know the binary notation of 2, 3 and 4. We know notation for 0, that is 0, 0, 0, 0, 0, 1 for 1, 0, 1, 0 for 2. So based on that, we give the output. So wherever we have 2, we label that as 1. Similarly 3, 4 and 5 in the truth table, we label as 1. Coming to the K map, when we plot this, we have M0, M1, M3 and M2 here. So wherever we write 1, in those positions for 2 and 3, similarly for 4 and 5, we give 1, 1 notations. And the rest we can fill with zeros. Over here it's not mentioned, we can just add zeros the remaining position. What are the remaining positions here? We have 0, 1, 2 and 6, 7 and 6. So this is the representation of the K-map. Now, how do you simplify this K-map is very important. So what are we going to do? In a K-map, we can simplify based on the hierarchy. We have a quad. First we have the oct, that is 8. Then we have the quad and then we have a pair. And if at all there is no match for it, we go for a single notation. So here we have okay. Here here we have 3 and 3 and 7. So this makes one pair. This makes one pair. So we go to the order, that is x0 and yz as 1 1. We write that. Similarly, we have x and yz as 1 1 1. 1 here, 1 1 here. So x yz and x bar and yz. We write those two terms as one pair, p1. Similarly, here the corner terms, this is 1 and this is 1. Together we get these two notations. Now, upon simplification, where how do you simplify it? If we have two terms, we can either cross out the complement terms and reduce it without any duplication. That is one way. And another way is taking the common factor out. That we can see when we have a quad or oct. It becomes much simpler to understand. So for this function, f x, y, z, 3, 4, 5, 3, 4, 6 and 7, we have this as a notation. Yz plus x z bar. From one pair we have x z bar, from the other pair we have y z. So this is about 3 variable K-map. Moving ahead, this is another example. We have terms 0, 2, 4, 5, 6. We go to the K-map. Wherever we have 0, 2, 4, 5, 6, we go for those, match it, find the pairs and write the notation. So here, more importantly, let us try to understand a 4 variable K-map. Here we have a 4 variable K-map. What are the 4 variables here? Let us take this example. This has a grouping too. Okay, we have 4 variables x, y, z and w. So 4 variables. As I stated earlier, 2 to the power of n, 2 to the power of 4, it becomes 16 and we have 16 cells or squares. Okay, so we write x, y, z and the remaining w here. And this is the given function. We need to take 0, 1, 2, 4 and so on, plot that in the K-map here. So first we have a 16, 4 into 4, 16 K-map, 4 variable. We have at number position 0, that is M0, we write 1. Similarly 1 and 2, that is 1 and this is 2. Similarly for the rest we fill with 1s. And the remaining we can have 0, 0, 0 as stated earlier. So now, interesting point here to note is that we have a gray coding at position here and position here. In a 3 variable, we have only gray coding at this place and not here because we had a single variable here, but we have 2 variables here as well as here. So we have gray coding here, that is 1 0 goes to the 4th position and 1 1 to the 3rd position. Similarly here it gets reversed, 1 0 here and 1 1 here. Now after plotting all these and filling the remaining with zeros, note we are only discussing about SOP expressions here. Okay, now we try to find the quad Oct and pair. Most importance given to the oct because it makes the equation even more simpler. That's it. So we have one oct here. As the cursor, as I'm moving it, we have one oct here. Now we have one quad here, this one, as well as this one, and the second quad being this one here and this one. So accordingly, we're supposed to write the expression which follows those. Now here, let us try to understand in a much simpler way by taking the common factors out. For this one, the first one here, this one and this one. See here, for this one, this cell and this cell, what's the common factor? 0, 0 and 1, 0. So 0 becomes a common, that is represented z bar, z bar. And here, these two, 0, 0 and 1, 0. 0, 0 being common here, it is represented by w. So we have w and z bar. Sorry, that is w bar and z bar, since it is 0 and 0. Here we have w bar and z bar. Now similarly, in the same way, we go for the oct, taking out the common factor between these two. That is again 0 here and 0 here, first two cells. So that is nothing but y here, yz, y. So we have y as a common factor, y bar as a common factor. Since it is 0, we write here y bar. Now this quad here, this one and this one. What is the common factor here in these two terms? Here we have 0, 1 and here we have 1, 0. That makes it okay. Here we don't have any common, so let's go to this one. We have 0, 1 and 1, 0. 1, 1 is common here, so we write z bar, and we have x as the common factor in the top row. We write x with z bar. Now here we arrive at the expression. So y, w, x, y, z, for these terms we get this as the expression. This is how we are solving the 4 variable K-map. On the next slide. Again a 4 variable K-map. The main idea is how we group it. In this we have also the don't care condition, which will be discussed in a much later stage. This is the don't care condition. So now let us try to understand what are the applications, what are the advantages of K-map. As stated earlier, advantages of K-map. Any Boolean expression, it becomes very complex while solving a 3 variable or 4 variable through techniques such as associative law or commutative law, De Morgan's law, by taking the common factor out and solving it step by step. So if we take an approach of a K-map for 3 variable and 4 variable, it's very easy. Just try to match with the quad, oct, take the common factor out, simplify it, and get the required expression. That is the main advantages. That is the main advantage. That is simplification. It makes a task of simplifying a Boolean expression much easier. Where do we find the applications of K-map? In most of the digital circuits, such as a decoder, encoder, multiplexer, demultiplexer, we are using the K-map to design the circuits, all the circuits, or any electrical equipment where we're dealing with gates, NOT gate, AND gate, XOR gate. We need the K-map for simplification, such as any watch or a LED display system which works on gates. We can use the K-map for simplification. These are the applications related to K-map. So now one thing which I want to discuss here. Okay, here looking at this example, suppose after simplification of the K-map, we get this as the expression. So now how do we represent this using the logic circuits? That is very important. So here it's given x bar y plus z. So first we take x as an input line, y pass it to the NOT gate, get the output, connect these two to the AND gate. That is one part. Next, we have already taken x, continue the same line downward, take the NOT gate, that gives you x bar. Similarly, we have the y bar notation, take that as a y before putting the NOT gate, go for multiplication, that is AND gate, and finally we have z, introduce a new z input line. So we have two AND gates here and one single z input line. Connect all these three to the OR gate to get the output line. So this is how we write the logic single expression circuit diagram for a given simplified K-map expression. So this was about K-map applications, advantages, what is K-map, what are the different types of K-map, a 4 variable more importantly, in the concept of binary coding, how we write it, the cells, the number of cells, how would we find the number of cells 2 to the power of n, those things, draw the truth table, and then a logic circuit. Simplification is based on common factors. How do we group it? Based on quads, that is an oct quad or a pair. This is all about K-map. Hope you found this informative. Thank you so much.